In this lecture, I am going to explain about that integral form of zero order reaction. Okay, so I am going to derive that integral form of zero order reaction K naught. Okay, so just here assume one of the reaction A gives rise to product is a zero order reaction. Okay, so we are assuming A gives rise to product is a zero order reaction. So for this, when you want to write that rate is equals to dx by dt, that is equals to minus d concentration of A by dt is equals to K naught concentration of A whole to the power of 0. So already you know that a rate equation, when you write in the rate equation for any reaction, so rate is equals to K naught concentration of A naught for this zero order reaction. Okay, exact a mathematical relationship between the rate and initial concentration of reactant. Usually we will be taking that a rate equation. So just I represent the rate, usually we will be write with the dx by dt, and also I express it in terms of that reactant minus d concentration of A by dt. So here you know that the negative sign can always represent the decrease in concentration of reactant. Okay, so just that's why I am given the total rate is equals to K naught concentration of A whole to the power of 0. What is the K naught? It is a zero order rate constant. Okay, zero order rate constant. So in zero order generally, so rate is directly proportional to concentration of A, initial concentration for any reaction except zero order reaction. Okay, so that's why I am given that K naught concentration of A whole to the power of 0. So here I would like to derive that integral form for zero order reaction. So for that purpose I am taking this equation minus d concentration of A by dt, that is equals to K naught concentration of A whole to the power of 0, nothing but 1. Just I am representing this one. So when you are sending the dA minus d concentration of A by dt is equals to K0 dt. Here I would like to do that integration on both sides. Okay, so integration on both sides. So when you are doing that integration on both sides, minus of integral d concentration of A is equals to constant outside of the integration K naught dt. Okay, so here I am doing that integration within some intervals. So at time t is equals to 0, I am taking that initial concentration A. After time t, the remaining concentration I am taking as a minus x. Okay, I am doing that integration between the time interval 0 to t with that concentration A to A minus x. So here you know that differentiation and integrations are quite opposite. So integral of differentiation of A is nothing but it gives that concentration of A. Okay, minus concentration of A. So what are the limits here? A to A minus x, that is equals to K naught. Here d integration get cancelled. What do you have? The t 0 t. Okay, substitute that whatever the limit values A to A minus x, upper limit minus lower limit, that is equals to K0 into t minus 0. So when I am giving that a minus, here what do you get? That A minus x is equals to K naught into t. Here what we need? We need K naught. K naught is equals to 1 by t. K naught is equals to 1 by t. A minus x. Okay. So K naught is equals to 1 by t. A minus x. So A minus x. What do you get? That K naught is equals to x by t. Okay. So integral form of a zero order reaction, it is possible to write within these two forms. K naught is equals to A minus x by t, or K naught is equals to x by t. Okay, so for this when you want to write that half-life for zero order reaction. Okay, so half-life nothing but we are giving that. Okay, so already I explained how to write that half-life, okay, in the previous first order reaction when I derived that. Okay, so just simple condition you can take that when t is equals to t off, then x is equals to a by 2. Okay, So this is the condition you can utilize to derive that half-life for any order. So here I would like to find out that half-life for 0 order. So I am substituting that x is equals to a by 2. Okay. So what you get that k naught is equals to a by 2. Okay. So t is going to become t of. So what we need here, we need t of. T of is equals to a by 2k naught. Okay. For 0 order, half-life is equals to T of is equals to a by 2k naught. So here you should bring one of the relation between the half-life and initial concentration. So what is that? T of is directly proportional to A. Okay. So T of is directly proportional to A. That means if initial concentration is going to increase, T of is also going to increases. If initial concentration is going to decrease, T of is also going to decreases. Okay. So this is the derivation of the integral forms of the 0 order and half-life. Okay. And also I am given some of the best example for that 0 order reactions. Okay. So all photochemical reactions usually we can give as a 0 order reaction. That's why I am given one of the reaction, best reaction H2 plus Cl2. Okay. In presence of sunlight we are given HCl. And decomposition of nitrogen dioxide on hot platinum surface, and the decomposition of ammonia in presence of molybdenum, and decomposition of hydrogen iodide on gold surface. These are the best examples, known examples for 0 order reactions. Got it? So this is a simple explanation about that and derivation of 0 order integral form and half-life. Clear?